In the last session, we have discussed about the quantum cascade lasers, and we have also seen how they are different from the conventional semiconducting lasers. So we also compared our solid state lasers of semiconducting lasers and the quantum cascade lasers. In quantum cascade lasers, we have a completely new direction, so where your conduction band is engineered such a way that the injection of electrons will take care of the lasing action. So these transitions, in the active regions you have a lasing action, and these are the regions or injection of the electrons. So the injection of the electrons across your device, so that the electron can be reused several times depending upon what is the period of the number of periods of your device. So each period is in this case roughly around 60 nanometers. So you have used this same electron roughly 60 times. Okay, so if your device have periods of 120 or more or 200, then you use the electron, same electron is 200 times. Okay, that means one electron is participating to produce 200 electrons, 200 photons. So similarly, you have many number of electrons have injected in your bias condition, so you have large number of photons can be achieved in a tiny device. So you are able to get milliwatts of power from your devices. Okay, so in this case it's completely electron dependent. So here there is no hole recombination is happening, electron hole recombination is not happening. It's completely unipolar, so that means the polarity is unique, like a single polarity is involved during these laser transitions. So that is a major difference between your conventional semiconductors to your quantum cascade lasers. Okay, as we've seen in semiconductor lasers, with the band gap plays a crucial role, because this band gap will decide you what is the output wavelength. So in the quantum cascade laser, your structure will decide the wavelength of the right as well as emission. So you can tune your structural design to get desired wavelength output. So you use the same material, you design the structures with the different widths, you are able to get the desired wavelengths from mid-IR to Tara's regime. Okay, so then we move on to fiber lasers. See, the fiber lasers are now, it's a current technology. So now current technology is moving towards the fiber technology. So though the fibers are invented long back, it's around 1960s or 61, we have a fiber lasers are invented, but those times we don't have any applications, because these optical communications, these are not in, still that time is infant stage. So these fiber lasers, though they invented very in the 60s, but now the technology is emerging towards the fiber lasers. Okay, though the invention is long, but large usage is not there, so that is why the technology is not moved in that direction. But now is the time comes for the fiber lasers. So now these are fiber lasers with a different fiber technology. You can make it, these fibers can withhold high powers. So now we can generate high power lasers using our fiber lasers. Okay, so the basic principle of fibers, we know, we follow the Snell's law. So once you talk about Snell's law, you have a rarer medium and denser medium. So your rarer medium is refractive index 1, and you have denser medium which is a refractive index greater than 1. When light incident, okay, from rarer to denser medium, we know that it will refract towards the normal. Now similarly, a light incident from rarer medium to denser medium, okay, if this angle is, okay, angle such a way that it provides that your light beam passes through this plane. Okay, so that is called critical angle. So now if your angle of incident is more than the critical angle, you have the light will be trapped inside your denser medium. That means again it will reflect back to your denser medium. So these are the basic principle will be work for the fibers. So that means like fibers or any waveguides, you have a waveguide design, so you enter more than a critical angle. So now what happens, the total internal reflection will take over, so that you can guide the beam. That's what these are called waveguides. You can guide the laser beam along the waveguide or a fiber is also a part of a waveguides. So this is the basic principle is used to guide the light inside the waveguides or fibers. So now these fibers are very much in use. For example, right now whatever our optical communications are happening through optical fibers. For example, now the world is connected through optical fibers. So we have optical fibers which are goes under the sea and oceans to connect the different countries. Okay, so now the entry point for our country is Mumbai. So optical fibers from west side it is connected to Mumbai. Then from Mumbai we have the transmission either through towers and through a cell towers or through a fiber cables we are getting to inside the country. Okay, from the east side from Mumbai to it will go towards Hong Kong to Korea and Japan. So this is connected in this region in this direction, and from the Pacific region through optical fibers from Japan to US it is connected through undersea. Okay, so right now our communication is happening, most of the communication is happening through optical fibers. So that is why our optical fiber technology is more important in the current situations. Okay, so now as you see you have a accepting angle. So for example, now this accept angle decides that so your angle of incidence is more than the critical angle. So now once you more than the critical angle, so you always have internal reflection. So now the beam goes through without any distortions. So still there is if you use a time dependent pulses, still when it passes through a optical fibers you have different losses. So that in this class we are not going to discuss those details, finer details, but in principle your optical fiber has core and cladding. So that means your core has different refractive index, that is N1, and cladding is different refractive index, that is N2. So you match such a way that the total internal reflection will be takes place through the fiber. Okay, so your accepting angle is also we call a numerical aperture. So that is your sin alpha will decide depending upon the refractive index you choose. Okay, so if you choose a proper refractive indices, you can increase your accepting angles. Okay, the total accepting angles is your 2 alpha. So now we have nowadays we have wide variety of optical fibers. So these are the step index fibers. So where you can see the refractive index variation is like a step. So you have the core as a N1 and your cladding is N2, refractive index is like a step function. Okay, so the variation of your refractive index is sharp at the edges. Okay, so now as you see in this figure, so your core is allowing different frequencies. Okay, that means it is allowing different modes into this fiber. So that means the core area is big, so that is able to allow different modes. So that we call multi-mode fibers. And in this case, as you see, your core radius is much smaller, that will allow only a single mode to pass through the fiber. So then you call it's a single mode fiber. Okay, so you can actually, depending upon the core size, you can either allow the different modes, or you want to restrict to single mode, so you can restrict the single mode by reducing the core size. Okay, so and nowadays now you can play with the different cladding and double claddings, so that you can increase the more absorption for your lasing actions. We have different wide variety of core sizes are available, and you have double cores and double cladding, and you have multiple cores, like for example like a photonic crystal fibers. So these technology is so like expanded, so now we are realizing that high power lasers are possible, and still we are able to increase the powers of lasers in the fiber technology. So now you see simple diagram of the fiber laser. So this is our gain medium doped fiber. So you have take a fiber and you dope the fiber with a gain medium, because for a lasing action you should have a precise energy levels, right, once to have a population inversion. So once this gain medium is only a possibility to have a population inversion. So that means now your fiber will be doped with the gain medium, whichever wavelengths you are interested in. Accordingly, those kind of materials can be doped into your fiber. So that gives it's a gain medium doped fiber. So then you have a cavity design. So like two mirrors here. So now these are the microscope objectives. You come with the pump. So in this case, I'm coming with the pump light. It's a blue light. So these mirrors are a dichroic mirrors. So dichroic mirrors means it allows one wavelength to pass and reflects one wavelength. Okay, in this case, for example, assume this mirror having high reflectance for the red light and high transmittance for the blue light. So that means it allows to enter the blue light, and then it will reflect the close to 100% the red light. So once you pump, so your pump light is collected through microscopic objective. So that means your fiber cores are micron sizes. Either you single mode or multi-mode fibers, most of the fibers of the core size of micrometers, you need to focus the light into the micron size. To focus your spots into micron size, generally we use high resolution lenses, that is called microscopic objectives. So when the light is focused into through microscope objective, then you couple into the fiber. So once your focused beam is coupled, so the beam size is persistent. So whatever the core size, the beam is expanded up to the core size. Okay, so then you have a total internal reflection. It goes through. So you have the fiber representation. That means it's like a reel. So you have actually bent your fiber many rounds. There are a number of rounds how you can bend. That means whatever the length you can decide by rounding up your fiber length. Okay, so now this doped fiber act as your gain medium. Okay, so now your photons, whatever the pump wavelengths, will absorb by the gain medium. Okay, so then you have a spontaneous emission, and this spontaneous emission is again collected through your objective, and it is reflected by this mirror. So this mirror having a partial reflectance, so that means that 90% is reflecting back like a feedback to your oscillator or a fiber oscillator, and only 10% will release. Now this is the first time this is spontaneous emission. Now these spontaneous emission photons will go back again, that will trigger the stimulated emission. So now you will start the stimulated emission, then you have many number of oscillations, then you amplify the beam. So finally the amplified beam will come out as a CW laser. So depending upon your materials you dope, either you get a CW or a pulsed, and once you have CW, we know that how to convert into pulse. Okay, so this is a basic principle of the fiber laser design. So now we have different semiconductor devices or quantum cascade lasers. we can have very tiny fiber lasers too. For example, this is your quantum cascade laser or a semiconductor laser. You can easily couple, because these devices are very tiny, the emission will be conical from your micron spot size, your micron scale devices. So this, for example, in QCL, a quantum cascade laser, your device is roughly in micron size. So now that is easily can couple to your fiber. So now this is the coupling of your semiconductor device to your fiber. So now your fiber is doped with the rare earth ions. Right now, whatever the gain mediums you want. Then as you see here, there are some grating elements. So these are called fiber Bragg grating. So that means these fiber Bragg gratings are act as a mirrors. So depending upon your fiber, depending on the wavelength you use, this wavelengths you can design the fiber gratings. So that will block completely to pass through, and it will reflect the light. For example, in this case, your red light will be not allowed goes back to the laser source side. It will reflect this direction, and this fiber Bragg grating is allowed to transmit few percentage of your lasing. So that means this is like a mirrors. These are mirror 1 and mirror 2. So your mirror 2 is designed as to reflect 90% back or 92% back. Okay. So now these fiber Bragg gratings are used as a mirrors in this fiber Bragg grating laser. Okay. So now you have a lasing emission. See, now we know that your fiber end is, your core diameter is few micrometers. So now you have a emission, a very conical emission is coming out of your fiber. Okay, now you see this, you collect your output is a conical emission. Now you can use a different collimating lenses to make the size of your beam. So depending upon your collimators, you can get the whatever the size of the beam you want. Okay, and the limitation for using this kind of a semiconductor laser as a pump sources, your output will be lower. For example, if you use a different pump lasers, that means, for example, now we have fiber couplers. So instead of one fiber, now you have different fiber channels. Okay, you use different fiber channels. Okay, so now you use different diode lasers to pump. So now you can increase the absorption. So similarly, you have a high spontaneous emission, then in turn you will get high stimulated emission. So that means you have high lasing action. So that way you have a high power we can get, or you change your fiber to higher order modes. For example, take your fiber with a bigger core. As I am showing is bigger core means like you will go 100 microns or 200 microns size. In single core fibers it ranges from 1 micron to a couple of microns or few microns. Okay, so multi-mode fibers you can have 100, 200 and 500 microns. Okay, so now this, anyway we have fiber Bragg gratings. This will allow only certain modes to sustain the cavity, fiber cavity. So now what happens? So though you can use high power lasers to pump. So as your fiber grating will not allow all the modes to enter. So this will allow only certain mode, whatever you require. You design your fiber grating accordingly. So then you have high pumping. So then you have a high optical absorption. When you have a high optical absorption, you will get high power lasers.